Welcome to my first video of the series on HVAC. This is just a basic overview on how HVAC systems work. Starting off, what does HVAC stand for? HVAC stands for heating, ventilation, and air conditioning, and it refers to the transfer of heat and airflow through the cab of a vehicle. When we talk about heating, heating is done using engine coolant or unused energy from the vehicle combustion process. Except for when we refer to electric vehicles don't have coolant systems, so they use a electric heater for heating inside of a cab. The heat from the coolant is released into the cab through the heater core. The heater core gets its heat from the unused combustion process, in which the coolant temperature is regulated through the radiator and also the thermostat, which controls the coolant flow through the radiator. The heater core chooses the amount of heat to let into a cab of a vehicle based on controlling the airflow through the heater core. The less air that flows through, the colder it's going to be. The more air that flows through, the hotter it's going to be. Air conditioning. Air conditioning changes the states of matter to cool the cab. This is a little bit more complex than just allowing heat into a cab through a substance such as coolant, where coolant acts a lot like water. Refrigerant is very much different, where refrigerant boils at really low temperatures. To understand air conditioning systems, it is important to understand the difference between two different forms of heats: sensible heat, which is the heat that can be measured with a temperature gauge, and latent heat, which is non measurable heat that is present through different changes of states of matter. In a good AC system, latent heat is present, converting liquids to gases and gases to liquids. Understanding how energy works, I have this little chart that I drew up where you have temperature on the y axis and energy on the x axis. When we get to a solid state over here, we get to a point where we heat up that solid enough for it to go into a liquid state, which it goes through a melting process. As you see here, as energy increases, there's this period where temperature does not increase at all, this flat line, but it's still getting more energy as it goes along. This is referred to as latent heat. This is sensible heat, this heat where you have this temperature increase when you have a liquid here, because the solid went from a melting point, now it's a liquid. Liquid will eventually get to a point where once we evaporate, we're turned into a gas. And again, you have this latent heat phase where you have an increase of energy, but not an increase in temperature. Same way going down. You have a gas and it goes into the condensing phase. It's losing temperature, but it's also losing energy. While it's going through its condensing phase, it's losing energy, but it's not losing temperature until it fully becomes a liquid. Once it's fully a liquid, it starts losing temperature. Again, that's sensible heat. And then it goes to its freezing stage, where it still loses energy while it slowly freezes, and it's losing energy as latent heat. Then, once it's fully frozen, it goes into its solid state in which it can lose energy. As far as this chart goes, the absolute zero, the lowest a substance can go, is referred to as absolute zero or negative 273 degrees Celsius or 0 degrees Kelvin. Kelvin is the proper scale when you're measuring temperature in scientific terms, but we always use either Celsius or Fahrenheit. I prefer using Celsius, but to convert Kelvin to Celsius, just take Celsius and add 273 degrees to it. The reason why the Celsius scale exists is because 0 degrees Celsius is the freezing point of water, and 100 degrees Celsius is the boiling point of water at atmospheric pressure. Temperature itself is kind of interesting because temperature is a measurement of the average velocity of molecules in a substance. It does not dictate the amount of energy that substance holds, just the average velocity of those molecules. When we go through how an AC system works, we start off with 4 different sections on a chart. I really like this kind of drawing. I think it kind of helps you picture it because I have the red side here's the hot side, the blue side here's the cold side, the light green here is the liquid, and the dark green is the vapor side. So coming from the compressor, keep in mind compressors work because they can only compress gas. If you try to compress a liquid, liquids are nearly incompressible. You can slightly compress a liquid, but you can hardly notice a difference in compressing a liquid. And if you compress a liquid with a compressor, it'll cause compressor damage. That being said, you start off with a compressor that goes from a low pressure gas and it compresses it into a high pressure gas. That high pressure gas goes into what's called a condenser. If you remember when we talked about the states of matter, we have the condensing phase when we have a going from a gas to a liquid. That's what a condenser does. It takes that hot high pressure gas, converts it into a hot high pressure liquid. You will have a temperature drop across the condenser. Usually you're looking at 20 to 40 degrees Celsius roughly. That's the loss of latent heat, the loss of heat through the lines, and also the loss of heat through the process of airflow, because you have ram air coming in through the condenser, which to note is usually mounted in front of your radiator, goes through that condenser. It'll slightly cool it, not a whole lot, but slightly cool it. So you're looking at maybe a 20 to 40 degrees Celsius drop in temperature from here to here. But keep in mind, this is very hot as is. This is still very hot. So you have this hot, high pressure liquid, and depending on the type of AC system you have what's called a TXV or a thermal expansion valve or an orifice tube. I'll get more into that in a different video, but just keep in mind they're basically like a restriction. So if you have a filter element on the high pressure side, that means you have a TXV system. If you have this filter element over here on the low pressure side, it means you have an orifice tube system. Coming from the receiver dryer, which is a filter element, it'll go into the orifice tube or thermal expansion valve. It'll lose pressure. So now we go from a high pressure liquid to a low pressure liquid. If you feel these lines are really cold. If you feel these lines are really hot. It's almost unbearable to touch either or. That's how much of a temperature change goes on. From these cold pressure lines, you get to the evaporator core. If you remember when we talked about states of matter, evaporation is going from a liquid to a gas. So the evaporator core goes with this low pressure liquid to a low pressure gas. Inside your cab, this is what actually cools your system. The temperature drop that you have this air that comes through here. When it changes states of matter, it absorbs energy from the air surrounding it. So you have that air that comes in to your vehicle. It'll absorb the heat, which is a form of energy, from that air, and it'll let colder air through that evaporator core. After the evaporator core, we come to the accumulator, which is only on orifice tube systems, and we go back to the compressor. An accumulator allows a storage of unused liquid refrigerant that made it past the evaporator core to save for future use and prevent the compressor from flooding full of liquids. That's why it's called an accumulator, because you have an accumulation of refrigerant droplets that are still liquid. On this chart, I have the dashed lines representing gas, and I have the solid lines representing liquid, the blue representing low pressure, red representing high pressure, light green representing liquid, dark green representing vapor. Put into the square grid. Ventilation. We talked about heating, we talked about cooling, but how do we regulate heating and cooling inside of a vehicle? It's done through controlling airflows through vents. There's many different controls that an air system will have, whether you're using things like defrost, face vents, feet vents, heating, cooling, and recirculation. For example, with a face and feet vent, you might have something where it's like this. You have an air coming in here. You have this little flapper valve, which might shut off air to your feet vent, but allow air to flow to your face vent. Controlling where this flapper valve sits controls where that air flows. If it sits in the middle, you'll have air flowing through both. If it sits up top here, you'll only have air flowing through your feet vent. When you have things like recirculation, air recirculation, you have fresh outside air, or you have already cooled or warmed cab air. If you reuse the same air that you have, you can cool it a lot farther than you had previously. So, in this example, we have a flapper valve, which they're called blend doors. You have this little flapper valve that shuts off air coming from the fresh outside, and it allows this already cooled air to come and you either re-go through your evaporator core or go through your heater core. And it's kind of like this, right? So you have your heater core air that comes through here. You have your evaporator air that comes through here. And you can mix them together to control temperature. That will be it for the very basics of how HVAC systems work. Thank you guys for watching.